All right, so today I'm going to be talking about crown fire hazard, particularly around silvicultural perspectives, as well as a couple of new ways that we can quantify fire hazard. Um, so yeah, so far we've gone through sort of the conceptual basis for how we might predict the ease of crown fire ignition or active crown fire spread. And a lot of the insights that we've taken from those lectures around canopy bulk density and canopy base height as being primary drivers of crown fire behavior have direct applications to silviculture and fuel reduction and restoration treatments. Um, so the context we're going to be kind of working within is kind of going through these guiding principles in terms of designing fuel reduction treatments that were laid out in Agee and Skinner and really form the basis of a lot of our particularly fuel hazard reduction treatments and in certain cases restoration as well. So in this paper, they lay out four basic principles that are maybe somewhat expected based on our current understanding of fire behavior. But so here they are. So they got these four principles. So the first one is to reduce fire hazard, we want to reduce the service fuels. That's going to reduce our potential flame lengths, which is going to reduce torching and also make those fires a little bit easier to control, um, whether that's control from a prescribed fire perspective or a wildfire suppression perspective. Um, Principle number two would be increasing height to live crown or increasing the stand level canopy base height. Um, the main effect there is that it's going to make torching and crown fire transition more difficult. The next principle is to just decrease the crown density, right? So make that tree to tree fire spread less probable. Ultimately reduce crown bulk density, which as we've seen will make it more difficult for an active crown fire to develop. And then the last principle is to basically preferentially retain or keep large trees of species that are resistant to fire. So principle number one, reducing surface fuels, right? As we said, the primary effect there is to reduce fire line intensity and essentially, maintain that intensity below a critical intensity for the ignition of the crowns, right? So that'll provide lower torching or less torching and make the fire a little bit easier to control. In the context we've been discussing, right, this is basically an attempt to keep our fire intensity below the critical intensity from Brand-Wagner 1977. We can reduce surface fuels in a lot of different ways. We can directly remove them from the site, which can be is pretty expensive in most cases. Really common would be to do pile burning, as we see here on the right, where we're taking surface fuels or maybe even taking some slash we've created in the treatment and piling it up and then coming in and burning it oftentimes during the winter. You can see a little bit of snow there in the background, but when conditions are wet and fire hazard is low, we'll come back in and burn those piles. Alternatively, you could use a broadcast prescribed burn like we see on the left there to reduce the surface fuel load. So then principle number two, increase the height to live crown. Right, so the primary effect here is to increase the intensity required for tree torching or crown fire transition. But do note that when you remove the understory or do a significant thin from below treatment, you're almost certainly going to be increasing the mid-flame wind speeds, right? Because there's a whole lot less biomass in the way, and so wind is going to be able to move faster through these stands. So that's going to increase the surface fire intensity. So we just need to keep that in mind when we're planning these treatments. And then additionally, you can also end up increasing the surface fuel load, right? As you cut out those trees, maybe we're leaving slash on the ground. You can actually see in this photo here that I took in a thin from below treatment in the Black Hills. There's a decent amount of small diameter slash there on the ground, which will increase the potential surface fire intensity if we don't do something about it. So once again, we need to either account for that when we're doing our treatment and expect maybe some higher surface fire intensities, or we could combine this with principle 1 to reduce those fuels. Once again, either broadcast burn under more moderate conditions, or piling the slash, or one thing that's also often done is mastication, and mastication doesn't actually reduce the fuel load. It's really just changing it into a little bit more of a compact wood chip kind of a fuel bed, which has some other implications. Could potentially increase soil heating. Once again, depending on burning conditions. But that's not actually removing fuel. That's just kind of putting it in a different form. But mastication is often commonly used in these kind of thin from below treatments that they're seeking to increase the height to live crown. And you end up with these stands like this one where it's fairly homogeneous looking, and there's not much in the understory, or very little vertical heterogeneity in tree size. So then principle 3, decreasing crown density. Primary effect here is to reduce the bulk density in the canopies, and therefore reduce the ability for crown-to-crown fire spread. Do note that these treatments can also influence the mid-flame wind speed, essentially a larger wind reduction factor, because there's less crown fill, there's less stuff up there causing drag. And then once again, this could also increase the surface fuel loading, because when we're doing this kind of harvest, hopefully we're able to take the bulls out and sell them, right, and try and make some money, or potentially at least offset the costs of treatment. But a lot of times, right, that slash from the crown is going to just get left on site, so we need to handle that. And so basically the idea here is that the change in canopy bulk density needs to be large enough that it can offset the potential for increased surface fire intensity due to the higher winds. And the last principle is in many cases, you could think of this as maybe even more of just an ecological objective, but we want to keep the large fire-resistant trees. That means that our fire effects for any given intensity are going to be less, just because these trees are a lot more likely to survive. Doing this does have some economic implications, and there are some places where this has caused some controversies with, diameter limits, where a forest might say you're not allowed to cut any tree larger than X, which has implications in that, these treatments are expensive, and sometimes we want to be able to sell logs, and obviously these large trees represent the greatest value in the stand. So if we're not able to cut them, there are some sort of trade-offs there, at least economically. You can get kind of restoration and economics butting heads. So overall, these principles we've laid out are somewhat straightforward to apply and design from a silvicultural perspective, and creating a prescription. Right, we need to think about how our prescription is going to change the canopy base height and the canopy bulk density. We need to carefully consider how we might change the surface fuel load depending on our logging and sort of slash approach. And then we also need to consider the effects of changing that overstory on environmental parameters, including wind speed, which we've discussed, but fuel moisture I haven't mentioned yet. But when we open up the canopy a lot, we will often result in lower surface fuel moistures, right? Because now there's more solar radiation able to hit the forest floor, which will dry out our woody debris and our needle bed a lot faster. There's sort of an additional potential of greater rates of spread in those cases because that solar radiation may allow for greater grass dominance, right? And as we probably noticed in our fire modeling, right, grass fuel models have much higher rates of spread than our forest litter fuel models. So just kind of all things to consider, right? Not necessarily good or bad, but just you know, things to think about when trying to apply these to reduce fire hazard. So when we're going through these different options, right, there's often this idea of what might be referred to as like a gaming approach, where basically we go into a program like FVS and we just kind of tweak our treatment prescription and we come up with a whole bunch of alternatives, and we kind of mess around with each one until we kind of figure out how to meet the objectives we want, right, by individually tweaking parameters in terms of our thinning density and our how we select tree sizes in terms of raising the canopy base height, and all those sorts of things. We can just kind of play with each parameter and basically game the system to achieve the results we want in terms of potential fire behavior. So here's just a little example of comparing the initial conditions in a particular stand to two different treatment options, right? And so we can see in both cases, right, our trees per acre is drastically reduced. Quadratic mean diameters and is going up, right? We have a larger proportion of large trees, or proportionately more large trees. Obviously we're reducing our basal area and our canopy cover because we're cutting trees out. Both cases are significantly increasing our canopy base height, reducing bulk densities. But in our thin from below without the follow-up prescribed fire, we are increasing our surface fuel load. So we would need to do some fire behavior simulations to understand the implications of that. Or if we follow that up with a prescribed fire, right, at least in this scenario, we maybe lose a couple of trees, but we get rid of a lot of that surface fuel load. Then we also notice that these treatments are increasing our wind adjustment factor, and remember, an increase in the wind adjustment factor actually means that our estimated mid-flame wind speeds are going to be higher. So we want to go ahead and link these structural changes to potential fire behavior changes, and we are going to do this through Behave. So we'll need to understand how treatments might change the surface fuel model, right? As I said, a treatment, in addition to maybe leaving behind a lot of slash we might want to account for, right, an increased fuel load. Over time, we might also expect a large grass or depending on the ecosystem, maybe even a large shrub response, right? So that would change the surface fuel model. We need to assess how the canopy fuel complex is going to influence fire behavior, and once again, right, we need those environmental parameters to plug into our model. So now here's our example again, but we're going to tack on our fire behavior stuff. So you can see how the fuel model has changed and how that's going to have some implications for the torching and crowning index, which are two ways to quantify basically the torching or crowning hazard. And later on in this lecture, I'm going to talk about those in more detail. But those are pretty common metrics to assess fire hazard. And then also we've got our predicted fire type under a 35-mile-per-hour wind. So basically what we see is in the case where we did not do a follow-up prescribed fire with 35-mile-an-hour winds, we'd actually expect to have an active crown fire, versus in our our prescribed fire example, the prediction comes back as conditional. And remember, conditional crown fire basically means that our crown base height is high enough that we wouldn't expect torching and then the initiation of a crown fire, but there is enough bulk density in the canopy that if a crown fire were to start, maybe a crown fire starts outside the stand and then moves into the stand. Conditional means that there's enough bulk density up there to sustain an active crown fire under that 35-mile-an-hour wind. So just trying to reiterate, right, when we're doing this, we got to think about all the changes to the fuel models, to the winds, to the canopy fuels, and link all of that together in terms of potential fire behavior. So there are a lot of different ways we could potentially quantify stand targets. One way is to use this equation here that's basically linking. It's basically just a modification of Van Wagner's crown fire initiation equation to basically find a target crown base height or canopy base height rather for our treatment. So the equation here, essentially we put in an estimation of the fire line intensity that we might expect, and as well as the foliar moisture content, and now we're solving for the canopy base height that we would need to target in order to prevent initiation under some set of conditions. So here's just a little example of how we could use this equation. So say we estimated that after the treatment, under some set of environmental conditions we're interested in, the estimated fire line intensity is going to be 300 kilowatts per meter. We'll assume our foliar moisture content is 100%. And when we plug those values into the equation, basically we get a target canopy base height of 1.46 meters. And that's just going to tell us that if we want to prevent transition, under these conditions, we would need to thin our forest to create a canopy base height of 1.46 or 1.5 meters or greater. So whenever we're doing this, right, we need to think carefully about the input values we select. Keyes and O'Hara call this intelligent decision making. Essentially we can predict fire line intensity from Behave, and when we're doing so, we might want to consider that there's been some suggestion that Behave under predicts fire line intensity. So maybe we want to be a little conservative and use a higher number there. And then we also need to understand that fire line intensity is associated with whatever the inputs we put in there. So a lot of times when we do this, we might want to use something like the 95th percentile weather conditions. So that would be like, the weather conditions for a particular site that are as extreme or more extreme than 95% of the days at that particular site. And then once again, there's this approach where now we're rearranging Van Wagner's criteria for active crown fire spread to calculate a target canopy bulk density. So basically the goal is to estimate the bulk density below which crown fire spread wouldn't be expected for a given crown fire spread rate. So there's the equation. Once again, that's just Van Wagner's equation rearranged. And remember here that ROS crown is going to be based on fuel model 10 with a wind reduction factor of 0.4, and then you would use the site based estimates for slope and wind speed and fuel moisture to calculate the expected active crown fire rate of spread under those conditions, and then you plug that in, and this equation will give us a target canopy bulk density for our thinning treatment. So in addition to to some of the considerations we just discussed in terms of changes to the winds and the fuel models, Reinhardt et al. Lay out some more things to think about when we are developing fuel treatments. So generally speaking, right, fuel treatments are really about, or often considered to be about changing the fuel conditions to make wildfire either less difficult to deal with, disruptive to society, or destructive, whether we're thinking about destructive to homes and infrastructure, or potentially ecology, depending on the case. And a lot of different groups have different ideas about what we should be treating for, and they may assume they're talking about the same thing, but a lot of times they have different ideas. So it's really important to have clear objectives when you start planning any fire hazard reduction treatment, so that the expectations are clear, and hopefully we can reduce some of these polarizations that happen between public stakeholder groups and managers in terms of expectations for treatments. So one main thing that's really important to think about and be careful with in your language is that no matter what we do, wildlands cannot be fireproofed. No matter what we've done to them, under the right conditions, it inevitably will burn. And in addition to that, it may burn in a way that we don't desire, basically because any system is going to have a failure point at which, if we were trying to prevent active crown fire, the only way that we can ensure that an active crown fire will never occur would be to clear cut the stand and maybe put in a Walmart or something. So obviously, we can't totally fireproof these stands, and it's important to not suggest that we are. There have been cases where people's language is a little wonky on this regard. So we can't fireproof anything. So sort of a follow-on is that fuel treatments are focusing on creating conditions where a fire can occur without negative consequences, or maybe with a lower risk of negative consequences. But the focus really shouldn't be on making conditions that are more conducive to fire suppression, largely because this is really an argument of circular logic, right? I mean, if our focus is on increasing fire suppression, what does that mean? Well, that means that we're going to let less acres burn, which is going to allow fuels to build up, and it's just this circular issue where if we enhance our suppression abilities, we're really just either perpetuating the current situation we're in, or making things even worse as we go along. So this idea has been described as the wildland fire paradox, right? This paradox between treating forests because the fuels have built up, but if we use those treatments to put out fires, the fuels are just going to build up even more. So we just kind of need to think carefully about why we're doing these things, and the goal shouldn't be all about increased suppression capacity. There's also sort of this widespread idea that the reason that we're doing fuel treatments, and if we do enough fuel treatments, that we can reduce area burned, whether by supporting suppression, as we just mentioned, or just by making forest conditions that are less conducive to large spreading fires. Once again, this is a little bit of circular logic, in that if we reduce area burned, we're just allowing more fuels to build up in those places that aren't burning, and really the long-term view is that fuel treatments aren't going to be sustainable unless they actually do the opposite and allow more sort of beneficial fire to burn, rather than reducing area burned. And then also this idea that, right, the focus is on reducing potential fire severity, but just because we've reduced fire severity, a fire is still capable of spreading through that stand. It just might do so at a lower intensity. So that's not necessarily going to change our area burned, just perhaps the the overall intensity and fire effects that we might see within that area. So then another consideration here is that sometimes people assume or talk about fuel treatments reducing fire rate of spread, and it's really not the best metric to look at. For one, the more important metrics are really about, well, what effects is that fire going to have on the site afterwards, which may or often are not directly related to fire line intensity. And then there's also just the idea that, we're kind of setting ourselves up for failure if we look at fire rate of spread, because in many cases, fuel hazard reduction treatments actually increase the fire rate of spread, right? They might reduce our intensity, they might reduce our effects and our torching and our active crown fire, but the surface fire rate of spread very well may go up for the reasons we've discussed before, right? There's potential for more wind in the understory. If we have a fuel type transition towards grasses and shrubs, that's going to increase our rate of spread. So it's really not the best metric to look at. It's better to look at things like, ecological impacts, and potentially some of maybe these crown fire indices that are going to be closely related to fire effects and ecological impacts. So there's also this idea that fuel hazard reduction treatments will reduce suppression costs. The analyses I've looked at certainly don't bear this out, and it's really because the suppression expenditures aren't necessarily directly related to the fuel conditions, but it's really about where the fire is, how many resources we put out there, which is often context dependent, right? If it's nearby, a large amount of development, we're going to throw a lot more resources at it. And really, if we want to reduce suppression costs, well, we need to suppress less fires or suppress fires less aggressively. And there's also this point that 85% of the money we spend on fire suppression, or probably even more, since that study is focused on 1% of the fires, right? These largest and sort of most fires that most directly impact development is really where that fire suppression is going. And so basically to deal with that 1% of really large fires, we would need to treat an extraordinarily large portion of the landscape, which just is not feasible through mechanical means. So once again, our best option there is to try and reduce suppression spending by letting some of these fires burn a little bit more freely when and where we can. Another point is that, fuel hazard reduction treatments aren't necessarily going to restore pre-European forest conditions, especially if our primary focuses are just on these metrics of torching and active crown fire potential. For one, conditions were really variable across time and space, across different ecosystems, and if we just have one target that okay, well, across this whole landscape we don't want active crown fire to be likely under the 95th percentile conditions, we're going to end up with just a really homogeneous landscape where all those forests look the same, with significantly reduced bulk densities and increased canopy base heights. But that's not what those ecosystems look like historically. There's a lot more variability at across scales where certain portions of the landscape were probably in higher hazard conditions, and so there's a one-size-fits-all approach is kind of convenient from a forestry and sort of management perspective, but if we're thinking about restoration, we need to allow for much larger range of heterogeneity than a purely kind of rule-based fuel hazard reduction sort of approach would leave us. So at least in this context, it's not that helpful to think about these being restoration treatments, just because we need to think about a whole lot more than just torching and active crown fire reduction if we want to truly do restoration. So as we've seen a little bit of, right, there are a lot of different ways we could we could try to basically compare or gain different silvicultural treatments, including behave, and we just need to be intelligent about how we're going about picking our variables when we're comparing treatment alternatives. So two really common metrics used to kind of compare treatment alternatives are the torching and crowning index, that both come out of this Scott and Reinhart paper that we've already seen, where they present their idea of passive crown fire rate of spread, and how to quantify that. And so the idea here is that basically, given the surface and canopy fuels and site characteristics, we can define some critical combination of dead, fuel, moisture. So our environmental parameters, right? So dead, fuel, moisture, and wind speed, that would result in either a surface fire, a passive crown fire, or an active crown fire. And basically based on the wind speed necessary to have those different types of fires, we can compare stands in terms of how resistant they are to either passive or active crown fire. So this figure here, right, it's basically showing us the different combinations of the dead fuel moisture content as a percentage of the dry mass, and the open wind speeds, right? So the combination of those two environmental parameters that result in different fire types in this given stand, right? And you can see basically as we increase our wind speed, at a given fuel moisture, eventually we move from surface fire into the passive crown fire range, and then ultimately into the active crown fire range. Basically how far up the wind speed bar that transition happens is a representation of how crown fire resistant that stand is, right? If we need a higher wind speed to achieve active crown fire, it's less likely that's going to occur, right? Because it's going to require a more extreme fire environment for it to make that transition. So based on this idea, Scott and Reinhart identify what they call the torching index. So the torching index is actually a wind speed, right? So the torching index is the 6.1 meter or the 20-foot open wind speed at which crown fire would be expected to initiate, based on the linkage that we've seen before between Rothermel's 72 surface fire model and Van Wagner's 77 crown fire initiation. So basically the torching index is going to be a function of our fuel model, or our surface fuel characteristics, the fuel moisture, the foliar moisture, the canopy base height, slope steepness, and then also the wind reduction factor, right? So this is an open wind speed, and so a denser canopy is going to reduce that wind even more. So wind reduction factor is built into the torching index. All right, so here is the equation for the torching index, and I'm not going to go through the whole derivation of this equation. You can look at Scott and Reinhart if you want to see basically how everything's pieced together here. But essentially, right, our torching index is equal to the open wind speed required for crown fire initiation, which is equal to this big, crazy equation here that's essentially done a lot of work rearranging Rothermel and Van Wagner in order to solve for that open wind speed. So yeah, we can look to Scott and Reinhart for this derivation rather than going through the whole thing right now. Similar to the torching index, the crowning index is also really just an open wind speed. So the crowning index is the open wind speed at which active crown fire would be expected to be sustained. based on Rothermel 72's surface fire model, and then linked through Van Wagner 77 criteria for active crown fire spread, and then the Rothermel 91 crown fire rate of spread model. Basically, the crowning index is just going to be a function of our fuel model, our surface fuels characteristics, surface fuel moisture, and then the bulk density of the canopy. Like the torching index, I'm not going to go through the whole derivation. We can find that in Scott and Reinhardt. But so here's the equation for the crowning index. And just to notice in here, we can see the things that are going to infect it, right? So the heat of ignition, which is going to be based on the surface fuel moisture primarily, our crown bulk density, or canopy bulk density, sorry, and then the slope of the stand, all go in there. So yeah, so there's our crown fire index, and the main idea to take away is just that this is predicting an open wind speed at which active crown fire would be possible based on the parameters of the stand and the particular weather conditions we've assumed. And then finally, we've got our classic assumptions and limitations slide. We've seen all these assumptions and limitations before because they're all just inherent to the models that were linked together to develop these indices, right? So they're making this assumption about homogeneity of the fuel, weather, and topography. Once this idea that we're only thinking about the quasi steady state rate of spread for a head fire, or in the case of crown fires, we're only thinking about the steady state spread rate for a wind dominated crown fire. We have no fire wind interaction on the convective flow or wind speeds. All these models are limited by the experiments that were used to derive them. Right, all the empirical constants in Rothermel and Van Wagner, and then our stuff related to how our wind adjustment factors are calculated, which we've talked about in many previous lectures. And then finally, this idea that we can use Rothermel 72 reaction intensity to plug into the fire line intensity as used in Van Wagner. Which might come with a little bit of under prediction, right? So we might find that it's a little harder to initiate crown fire than might be true in the real world, at least based on a couple of empirical data sets. So yeah, just got to keep our model assumptions in mind when we're using these indices. They're still really widely used. And one idea behind them is even if maybe you don't buy this IR to I relationship, or you've got a problem with some of the other assumptions, is even if you don't believe the true value, like say our analysis tells us that the torching index for a particular stand is 30 miles an hour. Maybe we don't believe 30 miles an hour, but we might accept that a stand with a torching index of 30 miles an hour is going to be, more difficult to initiate than a stand with a torching index of 5 miles an hour, right? So we can still make these sort of relative comparisons of hazard, even if, we're not so sure about the exact values or some of the assumptions underlying these models.